Prajwal Gowda, Ramesh, Ratan,
Present, sir.
okay, Rohan, Rutik, Rutvik, Gune, Rutvik, Sadashiv, Sagar, Sai Prakash, Samir Ahmed, Sania, Sanjay, Sankalp,
Present, sir.
okay,
Present, sir.
right, Sanket,
Yes, sir.
okay, Shiraj, Shivnanda Natikar, Shraddha, okay, Shubham, Sumit, Sai, Suraya Banu, Tejas,
Present, sir.
okay, Vivek, Yamunappa, Gaonkar Rajat Ramchandra, Manjunath Meligeri, Pratmesh, Joslino, Soham, Atiya, okay.
Sir, roll number 11.
Name?
11, Prajwal, sir.
Prajwal Gowda, right?
Yes, sir.
I have marked yours. Okay. Then Kirti, what is your roll number? Kirti, marked. Then Sai Prakash, what is your roll number?
19, sir.
19. Okay. Anybody else? Right. In the last class, I discussed about the Miller's theorem. We discussed about the Miller's theorem in the last class. It is Miller effect capacitance. And considering the inverting amplifier and the loading effect, we derived the formula for the Miller's input capacitance, that is CMI is equal to 1 minus AV into CF. Similarly, for the output side, we derived the formula considering the loading effect, that is CM naught is equal to 1 minus 1 upon AV into CF, Miller's output capacitance. Then for the non-inverting amplifier, the formula will be CMI is equal to 1 plus AV into CF, CM naught is equal to 1 plus 1 upon AV into CF. The formulas will get modified slightly for the non-inverting amplifier. This is what I have mentioned here, CMI 1 plus AV into CF, CM naught is equal to 1 plus 1 upon AV into CF. This is next, that is emitter follower configuration. Now for the emitter follower configuration, we have already studied the RE model of the emitter follower configuration. We are considering again the same RE model here. Are you able to see the screen, students? Screen is visible?
Yes, sir.
Right. This is the emitter follower configuration. We have already studied the RE model of this. Now we know what is emitter follower configuration. In the emitter follower configuration, there is only the base resistance and the emitter resistance. There is no collector resistor present. Okay. the emitter follower configuration, we have only the base resistance and the emitter resistance. Input voltage is applied to the base terminal and output is taken from the emitter terminal. That's why here in the emitter follower configuration, the output at the emitter follows the voltage at the input or the voltage at the base terminal. Therefore, this circuit is called as emitter follower circuit or the emitter follower configuration. We have input voltage Vi, input current Ii, input impedance Zi, input capacitance is C1, output capacitance is C2, base resistance is Rb, VCC is the supply voltage, then the emitter resistance is Re, capacitance at output is C2, output impedance is Z0. Then we have the current flowing into the terminal here, into the emitter terminal, that is I0, according to our convention of the two-port system. Then we have HIE and HFE. Now, for this emitter follower configuration, we have already gone through the RE model of this. So we know we have drawn the RE model of this, right, in our second module in the beginning classes, where we have drawn the AC equivalent circuit and then the RE model, right? So whatever analysis we are performing in the module 2, it is all AC analysis. We know that we have almost come to the end of the module, and in module 1 it is only the DC analysis. In module 1 we are studying only the DC analysis. In module 2 it is all the AC analysis, right? So here when we perform the AC analysis, we get the AC equivalent circuit. From the AC equivalent circuit we are getting the RE model. So I am drawing that RE model here, that RE model for the emitter follower configuration. We have the base resistance RB, right? Then here beta RE will come, because it is common emitter configuration. Beta RE will come from the AC resistance RE, that beta RE portion. Then here we have the resistance RE of the emitter resistance at the emitter terminal, that will be coming here. Then the collector current, it is flowing. We have emitter here, base here, and then collector. Collector current is beta into IB. This is the collector current which is flowing here. It is beta into IB. We know the beta relation, which is nothing but the ratio of the output current to input current. Output current upon input current, that is, here we are getting IC is equal to beta IB. Okay. Then here we have the emitter resistance RE, right? Current flowing into the terminal, emitter current, output current, it is I0. Then emitter current that is flowing here from the base and collector current, whatever emitter current we are obtaining, IE is equal to IB plus IC, that is flowing through the RE resistance. We have the input impedance Zi, which is seen from the input terminals, positive and negative voltage terminals, input voltage terminals. Then ZB is the impedance seen at the base side here. On the base side, whatever the impedance is seen, that is the base to, that is emitter. Base to emitter, whatever impedance is seen, that is the impedance ZB. Then we have the output impedance Z0, which is between the collector to emitter, collector to emitter. Output voltage is V0, right? We know the relation between the hybrid model and the RE model. In the RE model, we have beta RE, and the same beta RE will become HIE, or it is equal to HIE in the hybrid model. And also beta is equal to HFE. Beta is equal to HFE. Beta is in the RE model, whereas in the hybrid model we have HFE. So beta is equal to HFE, right? This is the relation that we have already seen when we are discussing about the relation or comparison between RE model and the hybrid model. Beta RE is equal to HIE, beta is equal to HFE. The resulting equations will be similar to what we have obtained already in the emitter follower configuration RE model. Whatever equation we have obtained in the emitter follower configuration RE model, the equations will remain the same. It is ZB is equal to beta into RE. In the emitter follower configuration RE model, we have got the equation for ZB as beta RE, beta into RE, capital R. It is emitter resistance, not AC resistance. That means beta is what? It is HFE. Beta is HFE. Therefore, ZB will be HFE into RE. ZB is approximately equal to HFE into RE. Then we have input impedance. Input impedance Zi is RB parallel ZB. These relations we have already obtained for the emitter follower configuration RE model. The same relations we are taking here, and we are just substituting the hybrid parameters. So beta is nothing but HFE. It will become ZB is equal to HFE RE. Then we have Zi input impedance as RB parallel HB ZB. RB parallel ZB. ZB is the impedance in from base to here, from base to emitter, that is ZB. RB is this resistance, which is connected to base terminal. Parallel combination of RB and ZB gives input impedance ZI. ZI is RB parallel ZB. Take it as second equation. And in the emitter follower configuration, the RE and small RE will come in parallel. We have the input voltage VI here, input voltage VI, output voltage V0. If we look into this circuit, here the AC resistance. So this RE and this capital RE will come in parallel when we consider the AC equivalent circuit. This RE and RE will come in parallel. So when this RE, AC resistance and the emitter resistance RE comes in parallel, because there is a junction here, so it is a parallel combination of RE and RE. On one side we are applying VI to the AC resistance RE, and on the other side we are taking V0, that is output voltage across the emitter resistance capital RE. Therefore it is a parallel combination of RE and RE, right? There is a junction here, there is a node across which the output voltage is taken, V0. Now this RE, it is nothing but HIE divided by 1 plus HFE. This RE is nothing but small RE is HIE divided by 1 plus HFE. How we are getting HIE divided by 1 plus HFE? How we are getting HIE divided by 1 plus HFE? That is, we can see here, we can check it. HIE divided by 1 plus HFE. HIE divided by 1 plus HFE. Right? Now let us express HIE. What is HIE in terms of RE model? Just now we wrote HIE is how much? Can anybody tell me? HIE is equal to how much in RE model? Comparison of hybrid and RE model. HIE is equal to how much? Yes, please. Beta RE. Correct? HIE is equal to beta RE. HIE in hybrid model is equal to beta RE in RE model. Therefore, here I will write beta RE. Beta RE in the numerator. In the numerator, it is HIE is equal to beta RE. This divided by 1 plus HFE. 1 plus HFE. What is HFE, students? In RE model, HFE is equal to how much? Yes, anyone? HFE is equal to how much? HFE is beta. Yes or no? HFE is beta in RE model. Therefore, write it here. Beta 1 plus HFE is 1 plus beta. Okay. So this I can further write it as beta RE beta RE we have beta RE divided by 1 plus beta is beta approximately. 1 plus beta is approximately beta. So write it 1 plus beta as beta. 1 plus beta as beta. Now here what will cancel? Beta and beta will cancel. This beta and this beta will cancel. Then what will remain, students? If these two will get cancelled, what will remain here? This is equal to RE, simply RE. Right? That is how we are getting HI divided by 1 plus HF is equal to small RE. Right? It's a parallel combination of small RE and capital RE. It's a parallel combination of small r and capital RE, but when we are drawing the hybrid equivalent circuit, that is approximate hybrid equivalent circuit, it will be HI divided by 1 plus HFE. That is nothing but RE in RE model. Clear here? So this is clear here, students, how we are getting this HI divided by 1 plus HFE as RE. Is it understood? Yes? Is it understood here, students?
Yes, sir.
Okay, fine. This Z0 is RE parallel RE, therefore RE parallel small r is HI divided by 1 plus HFE, or 1 plus HFE is approximately equal to HFE. Therefore, we have Z0 is equal to RE parallel HI divided by HFE. Z0 is equal to capital RE parallel HI divided by HFE, because 1 plus HFE is approximately HFE. Next, voltage gain equation. So we got the equation for output impedance. Z0 is RE parallel HI by HFE. Next, voltage gain. Voltage gain is obtained, AV equation is obtained applying voltage divider rule to this figure. So if you apply voltage divider rule to this figure here, we will get the output voltage. What is the output voltage? Is the main voltage VIE into resistance of the same branch, that is RE divided by sum of the resistances RE plus HIE by 1 plus HFE. What is voltage divider rule here? We are applying voltage divider rule to the output terminals, V0. Therefore, output voltage V0 is equal to main voltage, that is VI, into resistance of the same branch, that is RE, divided by sum of the resistances, that is capital RE plus HIE by 1 plus HFE. That is what is written. V0 is equal to RE into VI divided by RE plus HIE by 1 plus HFE. 1 plus HFE is approximately equal to HFE. Therefore, this equation gets modified as AB is equal to V0 by VI. This VI will come to the denominator. It will be gain equation V0 by VI. Therefore, AV is equal to V0 upon VI. That is approximately equal to RE divided by RE plus HIE by HFE. This is the final equation for the voltage gain in terms of the hybrid parameters. Similarly, we have current gain equation, which we can express in terms of the voltage gain equation, that is AI is equal to minus AV into ZI divided by RE, where AV is RE divided by RE plus HIE by HFE. So students, we wrote the equation for first one for the, it is for the emitter follower configuration. We started with the circuit, then RE model. We wrote the equation for input impedance RB parallel ZB. Then next, output impedance Z0 is capital RE parallel HIE by HFE. Voltage gain AV is RE capital RE by capital RE plus HIE by HFE. Then current gain AI is minus AV minus voltage gain into ZI divided by capital RE. These are the various equations, that is performance parameters of the emitter follower configuration. Is it clear here, students? These equations are clear here? Yes, please. Equations are clear here, students? Any doubts here? Understood this emitter follower configuration?
Yes, sir.
Fine. Okay. So with this, we come to the end of module 2. Today, I'll be starting with the module 3. Module 3, multi-stage amplifiers. Multi-stage amplifiers. The name itself will tell that it consists of many stages. Multi-stage. Multi-stage means many stages amplifiers. Amplifiers which are having more than one stage. Such amplifiers are called multi-stage amplifiers. Right? We'll see that what is meant by actually multi-stage amplifiers. Now, why this is required? Why multi-stage amplifiers are required? Now, whatever gain we are getting from a single stage amplifier, till now, whatever we have studied, they're all single stage amplifiers. We have used a single block, a single circuit, a single transistor, right? So that is a single stage amplifier, a single input and a single output. So such circuits are all single stage amplifiers. But if we are connecting one such circuit to next circuit, similar circuit, right, then it becomes multi-stage. If we are connecting two identical circuits and if you are applying output of one circuit to the input of second similar circuit, then that is called as the multi-stage amplifier. Like this, we can connect n number of stages, to get multi-stage amplifier. The question is why this multi-stage amplifier is necessary. The gain that we are getting from a single stage amplifier is not sufficient sometimes. The gain we are getting from the single stage amplifier may not be sufficient for certain applications. Therefore, what we have to do then, we have to connect many such circuits in cascade. We have to connect many such circuits in cascade. Cascade means output of one stage applied to input of second, then output of second is applied to input of third, output of third circuit is applied to input of fourth circuit, like this. We are connecting in the form of a cascade, just like how the bogies of the train are connected. Just like how the bogies of the train are connected, in a similar fashion, we are connecting the many amplifier circuits, many such stages of amplifier circuits to get higher gain, which will be useful for certain applications. And another reason may be input and output impedance may not be sufficient. Sometimes whatever input and output impedance we are getting from the single circuit may not be sufficient. Therefore, when we connect many such amplifier circuits in cascade, the input and output impedance will be boosted. That is, they will be increased. These are the two reasons why we are going for the multi-stage amplifiers. And cascade of common emitter and common base stage, it is called as cascode amplifier. Cascade of common emitter amplifier and the common base amplifier is called as cascode amplifier. Right? We'll see what are these next. This is how the different amplifier stages are connected. This is the first amplifier stage, which is having the gain of AV1. Its output is V01 and its input is VI, main input VI. The output of this amplifier is applied as input to the second amplifier, next amplifier. Okay, its input is Vi2. That means the output of first amplifier is applied as input to the second amplifier. Therefore, V01 will be equal to Vi2. That is, output of first amplifier is equal to input of the second amplifier. The main input impedance is Zi, that is Zi1. It is taken as Zi1. Output impedance of first stage is Z01. Then input impedance of second stage is Zi2. Then output of the second amplifier is V02. Output of second amplifier is V02. It is applied as input to the third amplifier. Input of third amplifier is Vi3. Therefore, V02 is equal to Vi3. That is, output of second amplifier is equal to input of the third amplifier. Output impedance of second amplifier is Z02. Input impedance of third amplifier third stage is Zi3. Then the final output, if you are consisting of only 3 stages, right? It's a 3-stage amplifier. There are 3 stages, 3 amplifier circuits. The final output, if you are taking it as V0 connected to the load resistance RL, then its output impedance we are considering it as Z03, that is the final output impedance. This is our cascaded system, just a simple cascaded system which is consisting of 3 stages. Okay. Output of a given stage is connected to input of next stage. Such an arrangement is called as the multi-stage amplifier. In above figure, we just saw that how the different stages are connected in cascade. Here, input impedance of what is the input impedance and output impedance of the circuit. The input impedance of the first stage is the input impedance of the cascaded system, and the output impedance of the last stage is the output impedance of the cascaded system. What is the input impedance here? Input impedance is the impedance of the first stage. Input impedance of the first stage is the input impedance of the entire circuit, that is entire cascaded system. And the output impedance of the last stage is the output impedance of the impedance of the cascaded system at the output impedance of the cascaded system. Getting the point here? Then these are the various input and output impedances, as I just now mentioned: Z01, Zi2, Z02, Zi3, then Z03, that is the final output impedance Z0. Note that here input impedance of given stage, it acts as a load for the output of the preceding stage. That means here if we consider Zi2, right, Zi2 will act as a load for the previous stage. If you just see this figure here, RL is connected at the output. It is acting like a load. It is a load resistance correct? Similarly, this input impedance Zi2 will act as a load for the output of the first stage. Then Zi3, which is the input impedance of the third stage, will act as load for the output of the second stage, will act as load for the output of the second stage. So this is how they are connected in the cascade fashion. Cascade system input impedance is that of first stage and output impedance is that of the last stage. That is Zi is equal to Zi1 and Z0 is equal to Z03. Since output of one stage is connected as input to next stage, we have Vi2 is equal to V01 and Vi3 is equal to V02. That is what it is drawn in the figure. Vi2 is equal to V01 and Vi3 is equal to V02. What is the total gain of the cascade system then? Total gain. If we want to calculate the total gain, then what we have to do is we have to multiply the gain of first stage into gain of the second stage into gain of the third stage. If we multiply the gain of individual stages, then we get the total gain of the cascaded system. If you multiply the gain of first stage into second stage into third stage, or if there are n number of stages, you have to multiply n number of stage gains. Then we get the gain of the entire system, entire cascaded system. The total or overall voltage gain of the cascaded system is obtained as like this. AVT, that is total overall voltage gain, it is V0 by Vi. Total output is V0 and total input, actual input that is applied is Vi. Therefore, total voltage gain is V0 by Vi. V0 by Vi. Now, this V0 by Vi can be expressed as in terms of the stages gain, in terms of the gain of the stages. Here it will be V0 upon Vi3. V0 upon Vi3, correct? That is for the third stage. Then next V0 upon Vi3. For the next one, it will be Vi3 upon Vi2. Vi3 upon Vi2. We are expressing the intermediate stages in terms of inputs, in terms of the input voltages. First is V0 upon Vi3, then Vi3 upon Vi2. That is the gain of the second stage. Then the gain of the first stage is Vi2 by Vi. Vi2 by Vi. That is, here we are multiplying these. Total overall voltage gain is V0 by Vi3 into Vi3 by Vi2 into Vi2 by Vi. What is Vi3? Here I have written Vi3 is equal to V02 and Vi2 is equal to V01. Vi2 is equal to V01. Therefore, total overall gain will be V0 upon V02. Vi3 is V02 into V02 upon Vi2 into Vi2 is V01 upon Vi. That is written here. Total overall voltage gain is V0 upon Vi3 into Vi3 is V02 upon Vi2. Then Vi2 is V01 upon Vi. V01 upon Vi. So it is V0 by Vi3 into V02 by Vi2 into V01 upon Vi. It is now written in terms of the intermediate outputs. If you look into this figure, it is V0 upon Vi3 into V02 upon Vi2, V02 upon Vi2 into V01 upon Vi. Getting the point here? V0 upon Vi3 into V02 upon Vi2 into V01 upon Vi. Therefore, it is important to draw the circuit, the block diagram correctly. Once we draw the block diagram this one correctly, so that we can easily will be able to derive the gain of the overall gain of the cascaded system. Therefore, overall voltage gain will be AV3, that is gain of the third stage. V0 upon 2 upon Vi2 is gain of the second stage. V01 upon Vi is the gain of the first stage. What is the total gain then? It is AV1 into AV2 into AV3, where AV1 is voltage gain of stage 1, that is V01 upon Vi1. AV2 is voltage gain of stage 2, that is V02 by Vi2. And AV3 is voltage gain of stage 3, that is V03 by Vi3. That is, total voltage gain is the product of the gains of the individual stages. This has been asked in some of the examinations to derive the total voltage gain formula for the cascaded system for the multi-stage amplifiers. So you have to start from the beginning, from this block diagram, right? And then go on expressing Zi, Zi1, Z0 is equal to Z03, then Vi2 is equal to V01, Vi3 is equal to V02. Write the equation for the total voltage gain in terms of the intermediate input voltages. Then Vi3 is equal to V02 and Vi2 is equal to V01. Express this in the form of this equation. In this equation, substitute. When we substitute here, we get total voltage gain as V0 by Vi3 into V0 upon Vi2 into Vi01 upon Vi. For n cascade amplifier stages, the total voltage gain is given by AVT is equal to AV1 into AV2 into AV3 and so on up till AVN. Right? This is about the cascaded system. In today's class, we have dealt about the emitter follower configuration, which we had already studied. We have taken the same RE model and we have expressed for the approximate, we have written the equations for the approximate hybrid equivalent circuit of the emitter follower configuration. That is, beta R is equal to HIE and beta is equal to HFE. Taking these comparison between the RE model and the hybrid model, taking these equations, we have obtained the equations for the input impedance, output impedance, voltage gain, and the current gain. Then later we started with the module 3, that is multi-stage amplifiers, where multi-stage amplifier is consisting of many stages. The gain of the total stage, gain of the overall cascaded system or the multi-stage amplifier is nothing but the product of the gains of the individual stages, AV1 into AV2 into AV3. For this, we have derived the equation. There we have derived the equation, that is AV3 is equal to AV1 into AV2 into AV3, where AV1 is V01 by Vi1, AV2 is V02 by Vi2, and AV3 is V03 by Vi3. For n cascade amplifier stages, if there are n number of stages, then the total voltage gain will be AVT is equal to AV1 into AV2 into AV3 and so on up till AVN gains. Okay, we are multiplying them. Is it understood here, students? Module 3, cascaded stages, you all understood the concept here? What is meant by multi-stage amplifier? This is the basic, that is fundamental. So if you all understand this, then the rest of the topics will be clearer to you. Okay. You should come to know what is multi-stage amplifier, why it is called as multi-stage amplifier, what is the necessity of the multi-stage amplifier, and what is the overall voltage gain of the multi-stage amplifier. How we are getting the overall voltage gain, how we are calculating the overall voltage gain of the cascaded stages or of the multi-stage amplifier. Is it understood here, students? Is it clear? Ankita, is it understood? Ankita?
Yes, sir.
Clear with this cascaded stages?
Yes, sir.
Okay. Janvi,
Yes, sir.
understood this multi-stage amplifiers?
Yes, sir.
Fine. Kirti Patil, Prajwal Gowda.
Yes, sir. Yes, sir. Understood, sir.
Topics are clear, Prajwal Gowda?
Yes, sir. Clear, sir.
Okay, right. Ratan, Birje,
Yes, sir. Understood, sir.
understood? Fine. Sai Prakash,
Understood, sir.
understood? Okay,
Yes,
good.
sir.
Okay. Sankalp,
Yes, sir.
Sankalp,
Yes, sir.
is it clear, Sankalp, today's topics?
Yes, sir. Yes, sir. Clear.
Fine. Sanket,
Yes, sir. Clear, sir.
Sanket, clear? Good. Shraddha, Tejas,
Yes, sir.
understood Tejas?
Yes, sir. Understood, sir.
Okay, fine. In the next class, we'll be considering the various circuits, the multi-stage amplifier circuits. That is, we'll be studying what is the cascode connection. Just I introduced in the introduction that the cascode is connection of the common emitter stage to the common base stage. If we are connecting common emitter and common base in cascade, Okay, then that is called as the cascode connection or the cascode amplifier. We are going to study that cascode connection, and later we'll also discuss about the Darlington connection. Okay, that is Darlington amplifier circuits. We'll take up those in the next class. Thank you.